In this video, we're going to introduce a new measure of how effective an amplifier is at making a signal bigger called power gain, which is relevant because we care about how power flows through S-parameter networks, especially amplifiers. However, we're going to skip the S-parameters in this video so that we can get a sense of power flows without worrying about complex math. We'll add S-parameters to our power gain analysis in a future video. One of the first things to discuss is the need for power gains at all. You've used amplifiers before, and we've mostly thought of a voltage source driving them, and the amplifier providing some voltage gain to that voltage source. For instance, this is probably how you learned to think about op amps. Voltage gains seem to work great up until now. One argument against voltage gains is that we've been examining how convenient it is to do math with power. That lets us avoid thinking about complex exponentials, and it lets us compare signals of very different power levels using logs, and that argument still holds water. But this first model hides some details, so we need a more detailed model too. Our first model presumes that the input impedance of the amplifier is really high, so that the amplifier doesn't load the voltage source. This doesn't work at RF because terminating a transmission line on an open will result in reflections, and reflections make designs complicated in a lot of ways. For instance, you have to care about the length of your cable. So instead, we'll usually want our source impedance and our input impedance to both match our line, which means dealing with the relatively low impedance level of 50 ohms. We have the same problem at the output. R out and RL are probably pretty close to Z0. Since we've matched our cables, we know eventually all our voltages will settle to levels that are consistent with a circuit where the cables don't exist. So we can find a loaded V out over V in using voltage dividers. And this loaded voltage gain is smaller than the amplifier's voltage gain of A. So we'd like to make sure our metric for gain takes account of source and load impedances somehow. The next question might be though, why isn't this loaded voltage gain good enough? Why go to power gain? And as I mentioned above, power gain is convenient because we can simplify our analysis by thinking about magnitudes and discarding phase information. It's also useful when the input and output have very different impedance levels, or when your gain is a current gain instead of a voltage gain. It winds up being a universal language across a lot of different types of amplifiers. However, we're going to hit a sticking point immediately as we try to calculate power gain. There are lots of ways we can define power. I've shown 4 options on this slide. The power that makes it into our network, so the power from the source, the power available from the source if Rin were matched, the power delivered to the load, and the power available to the load if it were matched to the output of the amplifier. You also may notice that I've omitted transmission lines from the schematic on this slide, and that's fine because we're going to be using this as a simplified example. So we'll just imagine that we're calculating power gains at DC where the transmission lines don't matter. And we'll include transmission lines when we think about power gains with S parameters later. So we've got these 4 different kinds of power that we might care about. Let's calculate the powers. So the first is power from the source, which is sort of deceptively named. It means power that makes it into the amplifier from the source. It's given by the voltage across Rin squared divided by Rin. And the voltage across Rin is set by a voltage divider attached to Vin, so we get a big squared ratio in this final expression when we try to refer our power back to Vin. Note that you could measure this value just by measuring V1 and measuring Vin, even if you didn't know Rin exactly. We'll also consider the power available from the source, which is the power that would come out of the source into the amplifier in the best case scenario where the amplifier is source matched. We know that a matching impedance is the best case scenario because of the max power transfer theorem. So since we know Rs and Rin are the same in this case, we know the voltage on Rin is Vn over 2, and squaring that shows that the power is Vn squared over 4Rin. And that's exactly half of the power that comes out of Vs, which again comes from the max power transfer theorem. We need to compare source power to the power dissipated in the load, which is given by the voltage across the load squared divided by RL. And we can relate this power back to V in by tracing through the dividers and the amplifier, which we do sort of in this step and this step and this step. The load voltage is set by a divider between the amplifier output V2 and Vout. V2 is A times V1, and V1 is given by a divider between V in and V1. Squaring all these gains and dividers gives a big sprawling expression for the load power. Finally, the power available to the load is the best case power delivered to the load when Rout is matched to RL. As with the power available to the source, half the power that comes out of the amplifier winds up in the load in this case. The equations I show here track some dividers back through the circuit to show a relation between power available to the load and V in. And you'll note that power available to the load depends on the RS to Rn divider because we only assume the load is matched when we calculate this power. Now that we have some interesting powers, which I've copied over from the last page, we can think about taking ratios of them to make gains. The first power gain is probably the most intuitive, power into the load divided by power from the source, which again could be rephrased as power into the amplifier. This is called power gain, or GP. And the expression for this is easy to find by comparing the PL and PS expressions and looking at terms that knock out. The V in squared terms cancel, Rn and RL become a ratio, and the RS to Rn divider cancels from both equations. So this term is here in PS and here in PL. We can also describe this power gain in words to try to make it easier to apply. The gain is the ratio of the power into the load to the power that makes it into the amplifier. Consequently, this gain doesn't account for the output power that we're leaving on the table by not matching the input. On the upside, it's relatively easy to measure by finding V1 and Vout. The second power gain we care about is called the transducer gain, GT, and it attempts to rectify some of the issues with GP. The expression comes from a ratio of powers on this page, and because PAVS assumes an ideal match while PL does not, none of the divider terms in PL cancel. So describing this gain in words, it's the power into the load, assuming the input is source matched. Or you could say that it's the power into the load divided by the best power we could get from the source. So because we're comparing our load power against a perfect input power, the best possible input power, this makes GT more pessimistic than GP. And GT also cares about both the input match and the output match, which helps us check whether or not the real system is living up to what you could get from PAVS. And so this definition is the most common gain reported in RF systems because it cares about both input and output matching. Finally, we sometimes would like to know the best power gain we could achieve for a given input power, and this is the available power gain, or GA. This expression contains an RS to Rn divider, which appears in PAVL. Because we assume matching at the load in PAVL, but not matching at the source, and we assume matching at the source in PAVS. So this gain winds up affected by the input divider because the power available to your load depends on how much you can get into the amplifier. So, said in words, this is the maximum power into the load, assuming the load but not the source is matched, divided by the best possible power into the input. So this forgives load mismatch and kind of is a gain that asks, what is the best I can get out of my network for a given power into it? So on the last slide, my thesis was that different types of power gains accounted for different types of matching. So perhaps it's unsurprising that all of these gains assume the same value if your system is matched at the input and the output. So if we assume Rs is equal to Rin and Rout is equal to Rl, we find that Gp, Gt, and Ga assume the same value. Each of the divider ratios becomes 1/2, and squaring that yields 1/4, and the 4 in Gt cancels out with one of the 1/4 factors. This quantity is called the maximum unilateral transducer gain, and you might note that you could also find it by dividing PAVL here by PS. And this is a handy upper bound when you set out to design matching networks. It's kind of one of the measures of what's the best I can do. So, in summary, power gain is important because it accounts for impedances of both sources and loads. We care about 4 powers: the power from the source into the network, PS, the power available from the source if the input is matched, the power to the load, and the power available to the load if the output is matched. And we care about 3 or 4 types of power gains. There's plain old power gain, PL over PS, which neglects the input mismatch. There's transducer gain, which is affected by both input and output matches. There's available power gain, which neglects output mismatch, since we're looking at the power available to the load on the numerator. And there's finally max unilateral transducer gain, this maximum available gain, that neglects both matches. It winds up being just a handy upper bound for us. And all power gains are the same if the input and the output are matched.